What's up, guys? This is Mr. O'Brien. In this lecture, we're going to be talking about metallic bonds and everything there is to know about bonding in metallic structures. So this information can be found in your textbook on on section 8.4. So let's go ahead and get started. So in your before we talked about this, I introduced a video about metallic bonding and how it is a bond between strictly cations, which may seem kind of weird because we're thinking about metallic bonds and thinking about cations that, hey, they're only like plus ions, right? So how do the plus ions like stay together supposedly in like this kind of like lattice, right? Because they're all positives. They should be repelling each other. So we start on by checking out this video about metallic bonds and how they're held together. So let's get started about metallic bonding. An important piece about metallic bonding is this idea of delocalized electrons. And here's a little image about delocalized electrons that you notice that they are um, valence electrons of the cations. But if you clearly observe the valence electrons and their behaviors, they're not staying put within their own electron shell. They're actually being moving around, right? The entire group of cations. And not just that valence electron, but everybody else's valence electrons are essentially randomly moving within the valence electron shells of others. And so it kind of creates this, what we call a sea of electrons within the metal. So in this metal that you see here, you're like, oh, it's just like a solid metal. But believe it or not, there are electrons that are constantly moving. So let's talk more about this idea of delocalized electrons. So why are these delocalized electrons present in metallic bonds? How is this able to happen? Well, you should know and remember that metallic bonds consisting of cations have really low electronegativity, meaning that they don't attract their own electrons and they don't attract electrons from others. So what they do have is an ionization energy that's really low that allows their valence electrons to be kind of let go, right? So the next question then becomes, well, how does a metallic bond stay together if they're all positively charged? Well, really, it's the metallic bond's attraction to the delocalized electrons. This Coulombic attraction, the attraction between pluses and minuses, really comes from the attraction to the electrons, not each other, but to the electrons. So it's like saying, like, you sit in a group of friends, right, in the classroom, but you don't sit in the group of your friends in the classroom because, say, you like them. What you like is the candies that they bring. So maybe everyone brings some sort of candy to the mix here. And because they bring candies, you're attracted to this candy, and you guys kind of share this candy all throughout the entire group. And you pass them around, and so it doesn't really matter like where you sit, right? There is no connection between each of you, your buddies. What you're connected to is those candies that kind of move around, right? If you can imagine that. So let's think about this in some sort of like question. So take a look at this image, right? And I want you to think about what you just heard. Um, what kind of metal would you think is in this metallic bond? And once you answer that question, what do you think that blue area, that blue shade kind of represents, right? So, what are some properties of metallic bonds that are associated with delocalized electrons? Now, think about metals in your own experience, right? What kind of properties, physical properties, do they have? Well, one of them is that they're really lustrous. They have a nice shine to them. And why do they have a nice shine? Because there's a lot of readily available free flowing electrons. And so the energies, like any light energy, can be readily absorbed by a lot of electrons here. And just like as you remember by the shine and emission of waves, you can absorb energy and then release energy as the electrons transition back to ground states, right? There's so many electrons available that they are very shiny. And some metals more shinier than others, right? Well, what else do they have? They're great conductors of heat and electricity. Make sure that you understand that conductors does not mean to make. It means to move, right? It means to move. So let's kind of view this and how is this possible? So imagine that you got to understand that the electrons are already moving in a metallic bond. So because the electrons are already moving in a metallic bond, it actually is really easy to heat and raise the temperatures of metals because they already have particles inside that make it move, that are already moving. So it doesn't take that much energy to raise the temperature of metallic bonds. And you can notice that the amount of energy needed to melt is quite different from the amount of energy needed to boil, right? Another example here of delocalized electrons being conductive. So when you apply an electric current, say like a battery, right, positive to a minus end, the electrons are being pushed out of this battery. This is the source of the electrons, and they go in one way as they push the electrons out and go out the other direction. Now, why does this do this? Because these electrons that move repel against the electrons that are already there moving already. So you can have this current that's able to be created using only metallic substances if you have a source of electrons. The idea here is that delocalized electrons are already moving. So consider this question about a property of metals. So the melting point of beryllium is about 1,287 degrees Celsius. But lithium is only 180 degrees Celsius. That's a big difference. It's almost like 10 times, right? Why do you think there's such a large difference in values to melt beryllium than there is to melt lithium? Why is it easier to melt lithium than beryllium? So consider that example. And if you have any questions, hit me up at tutorial. So what are some other properties? So they're very malleable and ductile, meaning that you can make into wires. Let's talk about the malleability first. Now, unlike ionic bonds, right, where in ionic bonds, remember that you have pluses and minus ions, right, that cannot touch the same ions. And if you knock them down, they'll repel each other. In this case, the malleability comes from the fact that these cations are not attracted to each other, but they're really attracted to the roaming electrons around. So it doesn't really matter what shape they're in or how they're in, as long as they still have access to some of these electrons that move around. Well, how is it ductile? Well, for the same reason as why they're malleable. Electrons are able to move. You can squeeze these cations kind of closer together and compress them in a way that you can get these nice fine wires just because the delocalized electrons are constantly moving, right? So what do they look like at a micro scale? Very similar to ionic bonds. They have these crystal structures to them, right, in the solid state. And each of one of these dots represents cations. Now, again, there is no anions, no anions present in a metallic bond. So what holds them together like so? It's the free moving electrons, the delocalized electrons, okay? So take a look at this example. We know that at room temperature, metallic bonds arrange themselves in crystal lattice structures. But there's an exception to this idea at room temperature. Can you think of that exception? Answer that question. If not, hit me up at tutorial. We'll talk more about it. And the last idea of metallic bonds is that you can actually create alloys. We saw a little kind of video about this, the Greek mythology of King Midas, right? He touches everything and turns to gold, right? But the idea behind that is that in Turkey, there is a kind of like a brass alloy present, and versus in Greece, there's more of like a bronze alloy present. And these differences come from the fact that brass and alloy, and you can kind of see brass looks kind of like gold versus bronze, and so hence this idea of the golden touch. Both of them contain copper, yet what makes this one shine a little bit differently than the bronze is that it's consisting of rather zinc than tin. And so an alloy essentially means that it is a metal that's consisting of different types of metallic elements, right? So that's the idea of an alloy. And there's a lot of alloys that you are aware of, and some we played in class, like in steel for the paper clips, and your in stainless steel utensils that you may use at home. So again, the idea of alloys is that these metal atoms can hook up together in any combination of metals, because again, the cations, if you recall, are only attracted to the delocalized electron. And so make sure that you understand that idea. If you have any questions, hit me up in tutorial.